All right, let's get started here. So yeah, let's do announcements verbally. Nothing really too much new. There's online homework is due this Friday at 11:59 p.m. That's the chapter 13 online homework. And then we have a new hand-in homework will be, well, it's actually up on Moodle already. And that'll be due next Thursday. So not this Thursday, but the 14th, November 14th. And that's up on Moodle. You can get started on that today or tomorrow or whenever. And then your tests will be handed back on Thursday in lab. So go to that so you can get your test back. And if you have any questions on particular grading of the questions, you can always come to me or ask your TA about that as well. Question? I didn't notice anything that stood out to me. The two versions were pretty close to each other, so I didn't. There were just some numbers changed around, so I didn't actually check this time like I did last time. And last time there was really no major difference either, so it just so happened in my two sections there were for some reason. All right. Any other questions? All right, so let's go ahead and get started. Okay, so now we're working with means now. So try to think back to what those the parameters and statistics were. Maybe we can just write them out. So we had statistic, we had parameters, and then we had let's see, mean, standard deviation, and proportion. So then with the mean statistic, we use the symbol y bar. And then we used mu for the parameter. Standard deviation, we'd use S and sigma. And with proportion, we use p hat and p. So we'll be using a lot more y bars and mu's and also s's and sigmas in this chapter. All right, so recall that we, in the last chapter, we were summarizing categorical data, so like yes, no, binaries, variables. And then now we're going to be summarizing quantitative data. So like height, weight, temperature, things like that. All right, so then what do you do if the variable of interest is quantitative and then the population mean mu is unknown? You can do a, well, pretty much you could do a estimate of it. But that's not always very good. You could do a confidence interval. So we again can use the central limit theorem to find what the sampling distribution of y bar will be like. And then we can see how that varies around mu, and we can use that to get our confidence intervals. All right, so then here, if we have a very low standard deviation, then all of the sampling distribution will be tightly packed, and then we would have a pretty good estimate of what mu could be. And then on the other side, if you have a large variation, maybe your estimate won't be as good. All right, so let's look at this example. So this is it's right skewed. Page 206. So distribution is skewed right. I'm just noting this because we want to work towards something that looks normal distributions, we're hoping. So the population here is the 383 UM students. So we can actually calculate what mu and what sigma are. So in this example, mu is 52.13 messages, and then sigma is 78.09 messages. So yeah, generally you wouldn't know those, but since we have the entire population's data, we can know that. All right, so now we're going to look at sample sizes. We're going to take some SRSs, so multiple samples. So those are random samples, multiple random samples. And then with n equals 3, 5, 10, and 25, and then see what the distribution of the y bars look like. So if you look on the next page, we can see some of these. All right, so the samples of size 3, we see that this is still pretty much right skewed. Samples of size 5, it's a little more normal, but still right skewed. And then I would say even for samples of size 10, it's still a little right skewed. But then by the time we get to n equals 25, it's looking a little bit more normal. So at that point, we could possibly use the central limit theorem in some sense, possibly. We need to discover what the central limit theorem says for means. It's pretty close, but it's a little different. So the three things here, it's pretty much the same thing as what we learned last chapter about proportions. So we've got, start off with the center. So the center is about, oh, yeah, I could. Maybe like that. A little bit more. Yeah, there we go. So the center is about, and let's look at here. So we've got, well, this one is kind of hard to tell. This one is a little easier to tell. It's about, this one it's about 50. This one it's about 50. And then this one, you can really see that it's about 50. So it's about mu equals, it was 52.13. So that's the same sort of thing as that happened in the last chapter. So our sampling distribution is centered upon the parameter. All right, and now we want to speak to the spread. So as n increases, the standard deviation of y bar decreases. So that's just saying that with larger sample sizes, these are getting more tightly packed, as you can see, these four. All right. And then the last one, it has to do with the shape. So as n increases, the shape becomes more normal. And you can actually find a formula for this standard deviation. And it turns out to be sigma over square root of n. That's what the standard deviation is using the central limit theorem. It just is that. All right. Questions with that? All right, so nothing too weird so far. It's kind of what you'd expect. So then, yeah, this central limit theorem can be used in many different situations. And in general, like a larger sample size means the better normal, the more normal the distribution will look. And then again, like in the last chapter, you want to use SRSs, so you need some kind of randomization, or else it's no good, because then you would have bias. Probably have some bias there. So this is arguably the most important result in statistics. So just stressing that there. All right, so here, can we see there? All right. So you would, just a little bit of note on the notation. So we have the mean of y bar, or E of y bar. That's the expectation of y bar. That's what that means. Expectation of y bar. And that's just a little bit of more statistics jargon right there. Just another way of saying the same thing. And it is this mu. And then here's the formula right there for the standard deviation of the y bar. It's sigma over square root of n. And then, so here's the central limit theorem, right there. So we have to have random samples. And then if you know mu and you know sigma, then you know that the sampling distribution of the y bars from the samples is approximately normal, mean mu, and standard deviation sigma over square root of n. That's the three things that the central limit theorem tells you. And then you also want to make sure that the sample size n is large enough. So in the last chapter, we used the whole success failure condition. It's not going to be the same thing this time around because there's no proportions. So we're not going to do n times p and n times q because, yeah, there's no p and there's no q. All right. So we need some different condition, a different condition here. In symbols, you can just write y bar approximately follows n mu sigma over square root of n. I can get my mu like that. Okay, so some things about this. We have a larger sample size, then the standard deviation gets smaller. And also, it becomes more and more it becomes more and more normal. So the central limit theorem is used to try to approximate what the actual unknown and what the sampling distribution of y bar is. So, right. And then here's the question: is how large of a sample size do we need? So it depends on how skewed the original population is. So some data it's very skewed, and then you would want to take a larger sample size, like 30 or 40. But then if the population distribution is already fairly symmetric, then you can use a smaller sample size, like 5, because there's not a lot of normalization that needs to occur, and then it'll look like a normal. So what you want to remember is that the 30. So you want a sample size of 30 or greater is generally what you want. But as you saw on the past, like 2 pages ago, n equals 25 was okay as well for that distribution. Right? So yeah, in general, just take sample sizes of more than 30, and that usually is good. But if it's like extremely skewed, you might need to do more. All right, so let's look at a confidence interval for a mean. Here, so yeah, we're going to make confidence intervals for something other than binary variables. That's pretty much what they're saying here. All right. So with quantitative variables, there are a number of different parameters we could be interested in. So we could be interested in mu, or the median, or the standard deviation, or the quartiles, or IQR. There's a lot of things we could be interested in. So yeah, the mean does not completely describe the population. So you would want to know a little bit more than just the mean. So remember how in the last chapter, if you knew P, you could find the standard deviation from P because the formula was square root of PQ over N. So in this chapter, the formula also involves sigma, not just the parameter mu. So, all right. So yeah, we need an SRS. And we're estimating mu from y bars. All right, so let's do an example with peanut M&M candies. All right, so what that says is says it's a net weight. So I brought some candies. Maybe we can zoom in here, huh? So you see right here, it's a net weight of 49.3 grams. So what that means is that the candy inside of the packaging is supposed to weigh that amount. So if it said gross weight, that would mean that the packaging and the candy would weigh that amount. All right. So net weight is the weight of the candy. And then what does it mean in practice? Like actually. So since these are peanut M&Ms, it's hard to get the weight precisely what you would want because some peanuts are larger than other peanuts. So maybe you get like 5 really large peanuts in this package, and then the weight is a little bit more. But it's not like they're going to like cut a M&M in half or something like that to get the weight correct, because that would cost, that would take too much time, it'd cost too much. And they're definitely not going to shave down the peanuts. That's just way too difficult. Why would you do that? But there has to be some way that they can actually get this weight, because you have to, there's rules about this. You can't just advertise that you're giving 49.3 grams of candy and it ends up being like 30 grams. Then you're getting ripped off as a consumer. So there's rules about this. So no, not every package has precisely a net weight of 49.3. Does every package have a net weight of at least 49.3? Well, we can try to decide that, to decide how likely it would be to get a weight of 49.3 or less. So yeah, so about the standards of the claimed net weights, we can look at that in chapter 15. So try to decide what the compliance level is there, because you could always have like a really rare specimen, and maybe it could be a little less weight. All right, so next page, what do we got? So we want to write what the parameter of interest is. And then we want to yeah, so we don't want to weigh every single, we can't weigh every single M&M package. That'd be too expensive. I can't afford that. So. All right, what is the parameter of interest? So the symbol now is mu, because we're talking about quantitative data here, the weights. And this is an average, not a proportion, so average weight in grams of all peanut M&M. Oh, I should have said net weight. It's net weight of all peanut M&Ms. I guess this is the 49.3 of the 49.3 gram I guess size. So like how big of a M&M bag, size bag. All right. And then the statistic will be a Y bar. And that will be the average net weight. In this case, we have 24. So we're going to say average net weight in grams of 24 M&Ms of the 49.3 gram size bag. All right. All right, so now So now let's record these weights, and then we'll use StatCrunch to find y bar and s. I don't know if you can see the screen. Maybe if I turn it. Yeah. Can you see the screen? I wish there was a trick for this. Well, I can always read it out, I guess. I think you can barely read that. All right. So what I did, I have a package. This is empty package, and it's saying 1.3 grams right there. So we want to subtract that off from the gross weight to get the net weight. So question. Oh, the tare? So you could use the tare. Yeah, let's just use the tare. Maybe that'll be easier. Yeah. Oh, you can't see it. I did put it in there. I don't know, how many decimal places do we need here? I guess it is 0.1 difference, so it is a noticeable amount there. So yeah, anyway, it's 1.3. We could just tare this. I heard tare and I thought it was a great idea. So like T-A-R-E. So let's tear off. So now with the packaging, it's a weight of 0. And then let's just go through these. So we've got 51.1, and I'm gonna be I'll just write this down. 51.1. That's 55.8. Uh, 52.4. This is exciting, guys. So we are gathering some data here. 49.3, and you're seeing there's a fair bit of variation here. 52.9. Let's just bust these all out here. So we got 54.3. You know what? I think this would go faster if I had a volunteer. Anybody want to volunteer to weigh these? Levi's got it. All right, come up here. Yeah, come up here. So I'll have you. Yeah, come around here. You can weigh these, and then just say out what the weights. Yeah, those are all weighed. That one's weighed, and then I'll just write these down, and then
49.2 grams.
all right.
$52.1 grams.
Oh, shouldn't have done that.
Good enough?
No.
Uh-oh. My bad. Okay. All right, sorry.
Oh, no worries. We're keeping track of you.
55.4 grams.
All right.
52.3 grams. 49.4 grams. 48.9 grams.
Oh, that one was below 49.3.
54.2 grams.
Yeah, I don't think we can quite see them.
52.2 grams. 54.1 grams. 53.9 grams. 51.7 grams.
Oh,
48.7 grams.
another low one.
53.2 grams.
And the last one. Huh? There you go.
48.0 grams.
It's our lowest one yet. All right, thanks, Levi. You could take one of these.
Oh, thank you.
Yeah. All right, so let's get this in StatCrunch. I'll type these in real quick. G1.1. I guess I should have typed this in when he was doing it. But. $49.4, 49.2, 52.1, 5.4, 4, 9, 54.2. And then I also weighed the one that was this guy, so that we get 24. What was it again? It was 52.2. All right, so let's look at a histogram. Right there. All right, so somewhat normal. We're suspiciously lacking in 50s. It's odd. If we look at the summary stats, variance, we have a mean of 51.89 or 51.9, a standard deviation of 2.22. All right. So now let's use that to decide. Well, we've got some issues here. Well, yeah, let's write this down here, and then I can we can get the rest of these candies distributed here using an SRS. So we'll use an SRS, and if you're here, good job being here. So, okay, so yeah, the Y bar was 51.9. Standard deviation is 2.22. C dot camera. See? Right there. Oh, these are in grams. It says remember units.